Aloha, my organic chemistry class. I love it. I'm so excited. We get to start one of my favorite topics in our Unit 2 section, and that is something called a mechanism. Now, there's a method to my madness. I would like to start mechanisms, which are a huge area of organic chemistry. In fact, they will be a third to a half of all of our next exams, as well as our exams in OChem 2. Mechanisms are huge for us in organic chemistry, and I want to start the foundations of mechanisms with a topic that you've already seen, and that's acids and bases. We've had acids and bases a little bit in general chemistry 1, a lot in general chemistry 2, so I want to start this new concept of a mechanism with something you've already seen quite a bit before. So you're probably wondering, what is a mechanism? This is literally our flow of electrons and how we explain how that reaction happens. Now, mechanisms are very specific. So our mechanisms are going to follow some rules. And they're going to be very specific in how we describe how that reaction happens. In fact, if you had a good General Chemistry 2 class, then the basis of our mechanisms actually starts in kinetics. So it's going to be really an interesting unit, our acids and bases. And in all my other videos, I gave you a million links to look at. But this section is really hard to do that because all of you are different. We're going to have pieces of Gen Chem 1. We're going to use things like bonding, Lewis structures, formal charges, and we're literally going to count electrons and use those electrons. So you may need to review that if your Gen Chem 1 is rusty. We're going to have a bunch of Gen Chem 2 topics. Specifically, we're going to use the language from kinetics. And that language is going to be really pretty specific. That language is going to use not calculating. We are not going to grab our calculator, but I'm going to use that language like second order, first order, things like that from our kinetics unit from Chem 2. So that might be something that hits the review list for you if you're a little bit rusty on that. Again, we're not going to calculate. We are just going to use that language. And then we're also going to hit a huge area that you likely had in Chem 2, and that would be your actual acids and bases, but they're based all on equilibria. You likely had an entire section of just equilibria. We will use the language of all of this. All right, again, we're not going to calculate, so no ice tables. But we are going to use that language. And then finally, one thing we're going to use in this class exclusively is a pKa table. So we are going to crunch some numbers, but it will be very visual. We're just going to look at our pKa table and see what it has to tell us. But we're again going to use the language and build on your skills from all of this. This is little pieces of Gen Chem 1, little pieces of Gen Chem 2, and then we're going to add our OChem 1 spin on it. So some of this really just happens to be your background. How much do you have to review? This is where that pretest comes in, y'all. You'll notice that all of these sections were in that pretest. So if that pretest, let's say you really struggled in the equilibria part of the pretest, well, then maybe that's something that you might want to review a little bit. Let's say you rocked bonding, but you totally sucked at formal charges. This section is why we took the pretest. We're hitting so much of our other chemistry classes in here. And then we're going to put our spin on it. So why don't we start with a reaction that I know in my heart all of you have seen before. And then I can really define what a mechanism is and show you our traditions for mechanisms, and then also do some nice reviewing and defining of acids and bases. I want to start with a reaction, like I said, I know in my heart we have all seen before, and that is hydrochloric acid. And you'll notice I'm drawing that full covalent bond and my lone pairs. And let's go ahead and react it with sodium hydroxide. Again, I'm drawing all of those bonds in full lone pair. And then we know, okay, hang on a second, what do we traditionally make with an acid and a base? We make a salt in water. Now this is one of our traditional, very early on acid-base examples. I love it. It is in fact going to be our first definition of an acid and a base, and we'll define that as an Arrhenius acid and a base. We're going to use this equation to actually define that Arrhenius acid and base. And then I also want to define our mechanism. In this course, we will have 3 different types of mechanisms. Our acid-base reactions are the first type, and those are called polar, meaning we're going to move 2 electrons at a time. In our next unit, we will see the other 2, and that is radical. You guessed it, that is 1 electron at a time. And then finally, organometallic. Okay, I love it. All right, so let's define both an Arrhenius acid and base and a mechanism. This is going to be wonderful. Okay, so if we want to actually show how this reaction happens, the first thing we learn is a kinetic study. The first thing we learn from that is that this reaction is second order. Okay, I love it. So you learned about your kinetics in your Chem 2 class. And what does second order tell us? It tells us a collision. Okay, well, why do we give a crap about that? What it's telling us is literally your acid and your base need to smack into each other in order to make our 2 products. So we take that to the next level in organic chemistry. We're going to take that information and we're going to add to it electrons. What are bonds made of? Electrons. So if you really want to understand how a reaction happens, you need to show making and breaking bonds. And not just, hey, this ends up here. You're going to literally track the electrons. If this base smacks into this acid and we have a collision, let's get even deeper. What makes the bond and what breaks the bond? And so that's what we call a mechanism. That's our flow of electrons. And we'll notice a pattern. We're always going to flow from where we have electrons to where we don't. So before I start any mechanism, this is what I love about acids and bases, because the information is there for us. We don't have to find it. Our information is there. We need to figure out where we have electrons and where we don't, because that's basic physics. You're going to go from where you have electrons or something's negative or partially negative to where you don't, where you have something that's positive or partially positive. That isn't Mother Nature's flow for those charges. So I'm going to analyze each one of these structures and look at where we have electrons. We certainly have lone pair around chlorine, and we have lone pair around oxygen. The difference is in that oxygen, we're carrying a negative charge. Okay, this is like a beacon in the night. If you've got a negative charge, you absolutely have electrons. In fact, you have extras. So this is our first place to start with that flow of electrons. You've got extras here. And then where do we not really have electrons? Of course, you've got a positive here in sodium, except let's go way back to your Gen Chem 1 on this one. Sodium, what kind of bond does it make? Does it make a covalent bond? Never. We are looking at an ionic bond. So what does that mean? That means we'll never form a bond to sodium. Sodium only gives away electrons. So we're going to kind of have that as a floater. This is going to be last in our little equation because we're not actually forming a bond to sodium, not a covalent bond. And our mechanisms are going to show us our covalent bonds and our electrons. So then we've got to take a look at that HCl. And if we add a nice polar arrow, we're going to notice that our chlorine is more electronegative than hydrogen, meaning that the electrons in this bond are really around chlorine more of the time. So that leaves a nice little partial positive charge on that hydrogen. Aha! Shut the front door. We've got electrons here in our base, and we've got a nice partial positive there on that hydrogen. So now, if you want to follow physics and you want to follow the laws of nature, what needs to smack into what? Let's get even more specific. We are going to take that OH. You've got extra electrons there. And when that smacks into your HCl, in fact, let's draw this just a little bit better. Okay, what if we then have a nice collision like this? What if that OH with those extra electrons literally collides with that hydrogen? Okay, now you notice I'm drawing an arrow there. This arrow is actually very specific. For polar mechanisms, we draw a two-headed arrow. That arrow is electrons. We are forming a bond to that hydrogen. So I'm going to color code 6 ways to Sunday on these things. So you may want to grab your colored pencils on this one. Okay, now we can't have two bonds to hydrogen, and that's what we've drawn. Something's got to give. When this negative oxygen smacks into that hydrogen, hydrogen doesn't have space to keep two bonds. So what happens is these electrons that are holding that hydrogen to chlorine in that covalent bond, they literally have to have a place to go. They are going to your chlorine. And that is okay because chlorine is far more electronegative than hydrogen. So what we just drew was our first mechanism. Now we're not quite done. We're going to notice that let's turn right around and draw what happens. So what did we just make with the OH? Okay, this stayed the same, but now these electrons are a bond to hydrogen. I love it. Aha, you just made your water. Okay, now what happened to chlorine? Let's draw it under here. Chlorine is not bonded anymore. We still had 3 lone pair around it. Now it has an extra, so it's negative. And then remember our floater that doesn't make covalent bonds. What kind of bonds does it make? Only ionic. There it is. It can float next to your chlorine. So what we just added to a reaction you've already seen a million times over was we added how that happens. We tracked our electrons and we drew what we like to call a flow of electrons. This is an organic mechanism. We will draw them to explain how reactions happen for the rest of the semester and all the way through OChem 2. It is an essential skill. I will bust out my color pens every time we draw one. And I want you to notice, look, this arrow turned into this bond. Look, these electrons ended up here. That's what our arrow does. These are sometimes called pushing arrows. Or pushing electrons. All of these are mechanisms. Okay, I love it. So let's turn around and do a definition then. I drew a classic acid-base example. And what did we make? We made water and salt. Okay, this is the original definition of an acid and a base from Arrhenius. This is back in the days when they used to just find new substances and taste them and see what their properties were. So that's how they could tell apart acids and bases, is that they literally tasted them. And acids, had a very, wait for it, acidic taste. And bases had a very basic taste, very alkaline taste. So how did they actually define an acid and a base? Well, if you'll notice, our acids had that hydrogen and our base had that OH. These are the two halves of water. So in any of these types of reactions, you made water. So the original definition to an acid is the formation of H+, right? That is your acid. OH- is a base. Now, this has been around for a very long time. This is definition number 1. We will have several. Let me spell it right. I got a little sassy and I was talking and not writing. This is our Arrhenius acid-base definition. So if we kind of picture this throughout history, this was the first easiest acid and base reactions. They happen very fast. They're very common. And you can taste them. I mean, please don't do that. I realize I just put out a video telling you to taste stuff. Please don't taste stuff. So you could tell the difference between a lemon and Windex. Okay, again, please don't taste them. But those are acids and bases. But here's what's sassy. So as time goes on, we start to discover other compounds and other things. Could other things be acids and bases? Absolutely. So let's take an acid and let's give us another one. How about HCN? This is a classic Chem 2 acid. I would be horrified if you had a Chem 2 class that you did not see that in. And let's see if we can react that. And then what's genius about a mechanism is that we can predict our product. In fact, let me give myself some space. Let me write it over here. So let's take cyanide and our same base. I'm going to color code because I love it. Okay, so we always start with where we have electrons. Where we have electrons will always be our base. So if we've got a base and we've got electrons, then by default, this is probably our acid, but let's take a look at it. Does CN have a little bit more electronegativity? Yeah, but it's a little bit more wimpy than our HCl. So what we learn in Gen Chem 2 is that there is a difference between these two acids. In Gen Chem 2, you would learn that this is a strong acid, and this reaction is not in equilibrium. What we learn in Chem 2 for this acid, for cyanide, is that this is actually a weak acid. And now we're in equilibrium. So we just want to, again, we're not going to calculate any of this, but we do want to use some of that vocab for equilibrium. You'll notice we're going to use that in this unit. So how do we react? It's going to be the exact same reaction. Where is my plus then? That positive, partial positive is on hydrogen. What has to happen in this reaction then? And you're going to notice a pattern. If we go from where we have electrons to where we don't we always go from base to acid? Yes. So let's take our base. It is a collision with your acid, and you're going to leave behind some electrons. Aha! Use your arrows now. Let's see if we can draw the product. Okay, again, our hydrogen, here's our base. That stays the same. We just formed a bond to this hydrogen. There's your water. I love it. Okay, now what happened to your cyanide? This part stayed the same. You just added some extra electrons. And then let's put that little floater in because that is only an ionic bond. So you just made a water and a salt, but this time you're in equilibrium. What's the difference and why do we care? When we're in equilibrium, we have to consider Ka. That's right. Remember all those tables you had in Gen Chem 2? But I'm going to slim it down. We'll use the language of Ka, but organic chemists love a pKa table, and we will use one in a little bit. So out of all those tables you learned in Gen Chem 2, we are only going to use a pKa table because it tells us everything. We don't need the other tables. We just need a pKa table. Okay. Yay, so exciting. Okay, so now let's go up a little bit in our definition because we still made water, so this is still an Arrhenius acid and base. We just have two types, strong and weak. And we're even going to monkey with that definition. I love it. All right, so what about our second then? As we kind of go through history, we could take our HCl again, and then we started to discover some other reagents that reacted with this acid, but they didn't have OH. So I know in my heart you've also done this in your Gen Chem 2 class where we're going to take HCl and ammonia. Okay, notice there's no OH in there. So what in the Sam heck is it? We already called HCl an acid because of that partial positive, but if there's no OH in there, could that still be a base? Yes, bases need available electrons, and you have a lone pair right there. Now our HCl, but you're going to argue, Dr. Morty, there's available electrons on that chlorine also. Absolutely. So what if you've never seen these two compounds before and you're wondering, well, which one is which? Aha, that's where we're headed. That's going to be a cliffhanger for a couple minutes, but that's where we're headed in this video. This video, I'm going to teach you the fourth definition of acids and bases, and that will be the winner. That's my definition. Okay, so as we go through history, they discovered these compounds that could act like bases, and they still reacted with acids. And how did that reaction happen? Our mechanism is exactly the same. You go from where you have electrons to where you don't. We can't form two bonds to hydrogen, so those electrons go back to your chlorine. And now this time, what did we make? Okay, well, here's your ammonia. You still have all three of those bonds on your ammonia. You just made another bond there. And you used the lone pair of nitrogen to do it. So is nitrogen neutral at this point? No. We have a positive on our nitrogen. We are now sharing electrons that nitrogen isn't used to sharing. This is a formal charge. So if this is rusty to you and you're wondering, Dr. Morty, why in the Sam heck do I have a positive on my nitrogen? That's Gen Chem 1. That's some of our bonding rules. Okay. And then what happened to chlorine? Okay, and I called that a formal charge, because we're going to balance it out. Is there a negative somewhere to balance it? Absolutely, right with your chloride ion, with that chlorine. So this is a salt. You just don't have water. Okay, well now this can't be an Arrhenius acid and a base. This has to be something else. So this is our second definition for acids and bases. And this is our Brønsted-Lowry. Oop, let's spell it right. Okay, our Brønsted-Lowry acid and base actually takes away the OH from your base. Our Brønsted-Lowry includes just that transfer of that H+. So you probably learned it as an H+ acceptor and an H+ donor. So basically your H+ acceptor is your base and your H+ donor is your acid. Now you likely saw these in your Chem 2 class. Okay, now as we work through there, I want you to notice that our mechanism's staying the same. We're going from base to acid. And we're color coding those arrows and they're showing us where our electrons go. So even if we get to a place where we don't know exactly what we're doing or we don't recognize one of our reagents, we're still going to be able to draw the equation, draw the reaction, and draw the product. That's the beauty of a mechanism. Okay, we've got 2 more definitions coming, but I've got to keep my videos pretty short or they're not saving. So I'm going to stop here and then we're going to pick up